So we said in the outline that we need to take 2 points that are very close to each other and find the difference in potential between the 2 points. For instance, what is VA minus VB or VB minus VA? 2 points that are separated by a very small distance. The idea of getting the difference in the value of a function when the variable changes only a small amount, we've done something like that before when we talked about how to get the area between two circles such that the radius only changes by a small amount. So the inner circle has radius r and the outer one has radius r plus dr. The thickness of the thickness between the two areas is very small. We've already done that before. So if you want the area for the radius r plus dr minus the area for the radius r, in the limit when dr is very small, when the thickness is very small. If the thickness is large, you can't do this in this way. But if it's very, very, very thin, the area between them is very small, the dr is very small, then we showed that you can get the difference in the areas. dA is the difference in the areas. You just take the derivative of the area with respect to r and multiply by dr. And you can see here, when you take the derivative of the area, you get 2 pi r. And so you get 2 pi r dr, which agrees exactly with the way of getting this area geometrically. And we've discussed this before in detail. So if you have any function of one variable and you want to get the difference in the value of the function at two nearby points, you just take the derivative of that function with respect to the variable and multiply by the dr. So that's the same idea we're going to do for potential. For instance, if you have a one-dimensional problem and you have point x and point x plus dx, and I want to get the potential at x plus dx minus the potential at x. So the potential difference between two very close points in one dimension. So it's the same idea. You're getting the difference in the value of a function between a value of a function at two nearby points. So you just take the derivative of the function with respect to x and multiply by dx. So that will give you dv. But the thing is that we don't have now a problem in one dimension. We actually have, our problem is in 3 dimensions. So you have point A, for instance, with coordinates x, y, and z. And then if you move a distance dx in the x direction and dy in the y direction and dz in the z direction, you arrive at another point B that's nearby with these coordinates. And we want to now get the difference in of the potential between point B and point A. These are two very close points, but now it's in 3 dimensions. So this is basically an issue of mathematics, this part. It's just if you have a function and you want to get the difference in the value of the function at two very close points, dv, what do you think it would be? Think about it for a while and see if you can figure it out, compare it with what it is in one dimension, and then proceed to the next slide. So there's a change in the potential when you move in the x direction. So partial v by partial x dx, that gives you the change in the value of the function due to the motion in the x direction. And there's also a change when you move in the y direction, and there's a change when you move in the z direction. If you add these three, you get the total change of the value of the potential between the 2 points. So the thing that corresponds to this in 3 dimensions, you just have 3 terms. So this gives you the difference in the value of the potential at 2 points, nearby points. Now you can start to see here how we're going to relate this to the electric field. I hope people can see that. I mean, take a look at this expression and think, can you see anything that looks like the electric field dotted into something else? Remember, the electric field is partial v by partial x with a minus sign in the I direction, partial bv by partial y with a minus sign in the j direction, partial v by partial z with a minus sign in the k direction. So already there's something here that we can try to fish out and see. This can be written in terms of the electric field somehow. That's what we want to find out. We want to know, if you know the electric field, how do you get the difference in potential between 2 points that are nearby? So what we got so far is the difference in the potential between the 2 points B and A, and we said it's equal to this expression. So let's just look at this problem a bit more detail. Let's zoom in a bit. Of course, all this is infinitesimal, but we're just zooming in to see how things are going. So you have point A and point B that we had before. And the vector dr that points from A to B, it has x component dx, y component dy, and z component dz. So we can write the dr vector this way. It's an infinitesimal position vector from point A to point B. And we know the electric field at point A. We said in this problem, we know the electric field. What we're after is the potential difference. So we know the electric field at point A. So if you look at this expression, if you take this in red is the electric field. So we're taking minus the electric field dotted into the displacement vector between the 2 points. Let's look at this expression and see. We'll see why we took this particular expression. It'll become clear. If you take the dot product between these two brackets, which terms survive? If you take the first term dotted into the first term, you have I hat dot I hat. I hat dot I hat is 1. So the first term dotted into the first term will survive. But the first term dotted into the second term, you have I dot j, which is 0. And the first term dotted into the third term, you have I dot k, which is 0. Now this for the second term, which one will the only term that will survive when you take the dot product of the second term with these 3 terms? You can show that it's only the second term that will survive, because then you have j hat dot j hat, which is 1. But when you take j hat dot I hat or k hat, you get 0. And the same thing for the third term. When you take the third term dotted into the third term, that survives, but when you take it dotted into the first 2, you get zeros. So the only 3 terms that survive from this dot product is this one dotted into this one, the second dotted into the second, and the third dotted into the third. And so when you do that, you get this, and you can immediately recognize what this is. We just showed a while ago what this is. This is the difference in potential between the 2 points. So this whole thing is just dV. And so that's what we're after. We're after the difference in potential between 2 close points in terms of the electric field and the position vector, infinitesimal vector that points between the 2 points. So this is what we were after, this kind of expression. So we found now what we were after, the difference in potential between 2 points, the potential at B minus the potential at A, which we write as dV B minus A. B minus A indicates that we're getting at B minus A. It's minus EA dotted into the vector, the infinitesimal vector pointing from A to B. Of course, you can write this in a different way by multiplying both sides by -1, and then in that case you're getting the potential difference between, you're getting VA minus VB. So if you just multiply by -1, this becomes dV A minus B, and then the minus sign goes here. So sometimes you'll find this expression with a minus sign, and sometimes you'll find it without a minus sign, depending on which 2 points are you getting the potential at A minus B or B minus A. And so let's do that and write it in terms of the potential difference between A and B. So this is dV A minus B, the potential at A minus the potential at B. A is the point where you know the electric field, EA. So the potential at A minus the potential at B is the electric field at A dotted into the displacement vector from between the 2 points. So this is the fundamental relationship that we're going to use. This is what we were after. And we'll see what the consequences are of this and understand it better in the next files.